technology of solar heating is very old. A patent for a solar heater was issued to Edward L. Morse in 1881. This patent also covered flat-plate solar collectors. To heat a house with solar energy, you can either apply solar hardware to a house, or you can build a solar house. The solar hardware typically includes collectors on the roof, a system to transport and store the heat, and a distribution system connected to the regular heating system of the house. In a cold climate, the annual heat for this house could be 75% from solar heat and internal gains, and 25% from fuel. For example, with an annual need of 60 million BTU, 45 million BTU could be from solar heat and internal gains, and 15 million BTU could be from fuel. The energy-saving benefit and the cost of such a solar heating system must be carefully analyzed. The costs depend upon the climate and the thermal needs of the house, and engineering, hardware, labor, profit, financing, and maintenance factors. An alternative is a solar house. The house itself can be an efficient solar collector storage unit. South windows of triple glass become the collector face. The collector operates at room air temperature with a low delta T to ambient. For example, with a room temperature of 70 degrees and ambient temperature of 20 degrees, the temperature difference, delta T, is only 50 degrees. The collector enclosure, the house shell, is superinsulated. Solar heat is stored in the interior mass of the house and furnishings. All of these factors make the house itself a very efficient solar collector and heat storage unit. On average, the solar gain of a south triple-glazed window exceeds the 24-hour heat loss of the window by 200 to 400 BTU per square foot per day during the heating season. Since windows are needed in the house for light, view, and ventilation, the solar gain of the windows provides free heat for the house. A south window has high solar gain in the winter and low solar gain in summer. South windows have the highest solar gain from October 21 to February 21, the 4 months which require about 80% of the heating season load. The solar feasibility of south windows can be analyzed. First, plot the solar gain of south windows for your latitude and climate, beginning with the maximum solar gain for single glass. This graph is for 40 degrees latitude. The solar gain may be as high as 1,500 to 1,600 BTU per square foot per day during the heating season. Each layer of glass reduces solar gain about 10%. The roof overhang is designed to shade the windows in the summer and to let sunlight into the house during winter. This shows the reduction in solar gain by the roof overhang. In the summer months, the solar gain of the shaded south windows may be only 100 to 200 BTU per square foot per day. While the roof overhang shades the south windows during May, June, and July, It allows some solar gain in spring and fall. In colder climates, a shorter roof overhang will permit higher solar gains in spring and fall. Using the percentage of sunlight for each month, the average solar gain of south triple glazed windows with a roof overhang is plotted. The average amount of daily sunlight for each month may vary from 30 to 60%, depending on the climate for the region. For this particular climate, the average amount of sunlight was 39% for December and 42% for January. The average 24-hour heat loss through the window is plotted for each month using room and ambient temperatures. Note that the heat loss of double glass exceeds the heat loss of triple glass much more than the solar gain of double glass exceeds the solar gain of triple glass. On the average, the solar gain of a south triple glazed window always exceeds the heat loss through the window. South double glass windows are effective in mild climates. Triple glass provides better performance in cold climates. In extremely cold climates, quadruple glass may be practical, especially in north windows. The maximum solar gain of south triple glass may be 1,300 BTU per square foot per day. However, with snow cover, the solar gain may increase to more than 2,000 BTU per square foot per day. In colder climates, snow cover is more prevalent, and reflected sunlight from the snow may become a large component of solar gain. Reflected sunlight through the south windows is also increased by water or ice-covered areas or by light-toned pavements to the south of the house. Therefore, since south-facing windows have a high solar gain in the winter and very low solar gain in the summer, a solar house should face south with a long south wall and most of the windows on the south. In the Illinois locale house, 85% of the triple glazed window area is on the south. In two-story houses and in mobile homes, all of the windows could be placed on the south. Small windows for view may be placed on the other walls. The thermal shell of a solar house must be very efficient to reduce the demand for solar heat and to retain heat. The solar house is a thermal house as well. With superinsulation, the U value of the ceiling equals 0.025. In extremely cold climates, with heavy snow, a steeper roof is better and allows for thicker ceiling insulation with a U value of 0.017. The U value of the exterior double-framed wall with 8 1/2 inches of insulation equals 0.03 and may be reduced to 0.025 for very cold climates by using 10 1/2 inches of insulation. The floor heat loss is less than 1 BTU per square foot per hour. This is achieved by a thermal balance of ground heat along with the floor and perimeter insulation. The U value of the triple glazed windows equals 0.38 or less. The shading coefficient is 0.82. Triple glazing may be a double glass window with a storm window having a removable screen. When sliding glass doors are used, both a double glazed unit and a single glazed unit are combined to achieve the triple glazing. The optimum south window area is about 8% of gross floor area. If deciduous trees provide for shade on the south wall in the summer, the percentage of south triple glass may be increased to 10% or more of the gross floor area. With a temperature difference delta T equal to 75 degrees, the design heat loss is less than 20,000 BTU for a house of 1568 square feet. The Illinois locale house was compared with a very good house built to HUD MPS standards. Using ASHRAE computations, the annual heating need was 62 million BTU for the HUD house and 40 million for the locale house without the inputs of internal heat gains or solar gains. The computer simulations used the U.S. Army Corps of Engineers Construction Engineering Research Laboratory Thermal Loads and Analysis Systems Simulation Program. Weather data were for Madison, Wisconsin for 1961, having 7564 degree days. Computer simulations compared the locale house and the HUD house. Internal heat gains were equivalent to 10 kWh per day and 2 persons, or 51,000 BTU per day. The air change rate was assumed to be 1/2 air change per hour. Temperature was allowed to vary from 68 degrees to 78 degrees during the 24-hour period, although the temperature rarely reached 78 degrees during the winter months. The interior mass of the house was assumed to be as much as 30,000 pounds for structure and furnishings. The roof projection was 30 inches outward and 16 inches above the windows. In addition to internal gain and solar gain, the HUD house needed 38 million BTU of heat for the year. With internal gain of 13 million BTU and a solar gain of 14 million BTU, the locale house needed only 13 million BTU of heat for the year with 7564 degree days. The internal gain and solar gain provided about 2/3 of the total heat required. Heat needed week by week is shown for the HUD house in the upper profile and for the locale house in the lower profile. The white area represents the annual fuel savings. The locale house and the HUD house could be built side by side to verify predicted performance. Auxiliary equipment. Small electric resistance heaters in each room would provide a low-cost heating system. Heat needed for space heating in the solar house could be less than the heat needed for domestic hot water. A water-air heat pump would have a high performance, providing substantial air conditioning and using the rejected heat for the preheating of domestic hot water up to 110 degrees. For example, as much as 9,000 BTU of house cooling and 12,000 BTU of water heating would be provided by 1 kilowatt of electricity. A small solar hardware unit would also be useful to heat domestic hot water. For a house with basement, a wall-mounted solar air heater could connect directly to the basement. What is the cost of a solar house? There are added costs for double wall, extra insulation, triple glass, and window reveals. The added cost of material and labor for the built improvements may be up to $2,500 for a house of about 1,500 square feet. There may be a saving of $500 or more on the heating and cooling system, which is much smaller than in a conventional house. Therefore, this solar house could have a net cost of about $2,000 more than a house built to HUD standards. A more general cost estimate for the solar house improvements would be from 3 to 5% of the total house cost. The annual energy saving should justify the investment, especially as fuel costs increase. In summary, a solar house may need only 1/3 of the heat needed for a conventional, well-built house. The house itself can be an efficient solar collector storage unit, truly a solar house.
I'm Ross Martin, Director of the Engineering Experiment Station and Professor of Mechanical Engineering at the University of Illinois. The tape you've just witnessed, we feel might be elaborated upon by some discussion. And I have with me a group this morning for that discussion. First, Professor Wayne Shick, who is Research Professor of Architecture in the Small Homes Council and Building Research Council at the university. Next, Bud Konzo, who is Professor of Mechanical Engineering in the field of heating, ventilating, and air conditioning. Next, Professor Rudy Jones, who is Director of the Small Homes Council and Building Research Council at the University of Illinois and Research Professor of Architecture. And last man on our panel, Warren Harris, who is Professor of Mechanical Engineering in heating, ventilating, and air conditioning area. Gentlemen, we've all, from the film, what would you say is the major message that we want to emphasize in this? Professor Jones?
Well, I hope that we have conveyed the idea that it's possible to gain great benefits from the sun as far as heating is concerned without the need for elaborate collectors, storage systems, and so forth. We have, through this study, convinced ourselves that a good thermal design of a house with proper orientation and attention paid to the arrangements of the windows in the houses and architectural features such as that, we can make a substantial savings in the amount of energy that is necessary to keep a house comfortable.
I think in that connection, Ross, that one of the things that impressed me about the study was the fact that the initial cost of a so-called collector system is so high at the present time that I think not enough attention has been given to how the size of that collector might be reduced by improving the house construction itself. And I think part of the worth of the Illinois locale house has been that there is a kind of a emphasis placed upon the construction, namely the insulation part, as well as on the new way of, not new way, but a different way of collecting the sun without the use of a collector.
It's a little unusual to look at the performance of a house over a whole heating season. Normally we calculate heating and cooling loads at the worst conditions, and Warren, you ran through, you made this calculation or followed the computer outputs of this, and what do you see as a related performance of the heating system that might best suit this home as auxiliary to the solar heating?
I don't know whether I follow you exactly, Ross, as to what you're after there. Obviously, the heating system is going to be much smaller than we're used to using because, well, we'll have to design it to take care of the day when there is no sun, but that's still only going to be around 20,000 BTU an hour, whereas the same house normally we'd think of at least 30, 35, 40,000 BTU an hour. One of the things that is of interest to me here and has been pointed out, but maybe not strong enough, that in using the solar house approach, we not only are making use of all the heat we can get from the sun, but by improving the house, we're getting a benefit in addition to that, even on cloudy days and at night, through the reduced heat loss.
Well, that was one of my points I was after here, is the low energy requirements of this house is a double benefit when you relate it with the sun.
I think Warren is right. The internal gains from the refrigerator, television set, the lights, the residual from hot water heating, all of these things can be retained within the thermal shell and be put to good use. Matter of fact, some analyses of this type have used much higher internal gains than we did in our computations. I have seen as much as double in some analytical designs.
So you're conservative in your
We think so.
estimates of internal gain.
Of course, it would be to the house's benefit to keep these internal gains down in the summertime so that you don't have a higher air conditioning load. And of course, a house can be ventilated by opening the windows in the overheating condition, which, by the way, could happen even in the middle of the winter. If you have a clear day, you could get more solar gain than you could tolerate, and you might have to vent a little.
That brings up one other thing in the design of this, the assumptions that were made in the analysis, that we chose a half air change an hour for the infiltration rate. You will find people that talk about even less than that. But our reason for choosing the half air change, we feel that about that much is essential just to keep the house fresh, to keep odors out of the house, to remove the moisture that's going to collect in the house. And that to maintain this half air change, we're probably going to have to ventilate part of the time because the house is tighter than that.
It's an interesting commentary that even with a half air change per hour, that's the single greatest heat loss in the house. All of the other items are smaller than that.
I have a table right here from some of these computer analyses that were made that we could reduce the air change to 3/10 of an air change, and we would reduce the energy required for heating from 9 million to about just under 5 million.
That was for an Indianapolis.
Indianapolis, yes.
Which
For an
of course
Indianapolis
is-
tape. We don't have it for the medicine tape yet.
That's considerably less degree days.
But it's about a 40% reduction.
A remarkable reduction. Of course, on this air change thing, Ross, you could increase your infiltration rate during the day if you got an overheat, as we've mentioned, but at night, after you've gone to sleep and there's no activity in the house, you might tolerate the half air change, or it might be even less with no
Even less,
doors being
yeah.
opened and so forth.
Yeah. Bud, you've done a lot of designing of heating systems. We normally think of 40 to 50,000 BTU type systems. When you get down to this small a unit, do you see any particular things that the heating and ventilating designer should be aware of?
Ross, this brings up some very interesting problems for the industry. Normally when we have, say, 40 or 50,000 heat loss, we consider inputs of 60, 75, or even 90,000 BTU per hour as normal, and most of the equipment sold is of that magnitude. When we get down to 20,000 BTU per hour design loss on a cloudy day or on a nighttime when the outside temperature is, say, 0 and the inside is 75, we're dealing with inputs of the order of 30,000 BTU per hour. In looking over the manufacturer's literature, I find there's very little in the way of equipment that is designed for this low heat loss. And along with that, of course, in the case of warm air heating, we have to have a fan that will provide us with what we call about 100-degree temperature rise of the air going through the furnace. And I think that this offers a distinct challenge for the heating industry to come up with a much revised and smaller and still efficient warm air heating system.
Heating unit? Mm-hmm.
I think the problem as far as the hot water system is concerned, and Warren can certainly add to that, it might be a little bit simpler, because I think some of their boilers are built for apartment use and are smaller capacity. Isn't that right, Warren?
That's right, as long as we say we're going to use gas as a fuel. If you're using oil, you're stuck. At the present time, we don't have a burner that'll take care of a smaller input.
Because of the smaller amount of liquid flowing through, it's hard to control.
Yeah, we just can't.
Yes.
Of course, we're talking about the smaller unit also in the air-to-air heat pump. That is, a 20,000 BTU unit would probably be over capacity for cooling.
Yeah. Well, as long as you mentioned electrical heating, I think the easiest way, not necessarily the best, but the easiest way of heating this house would be by electric resistance heaters.
Panel heater.
Panel heaters, perhaps, or baseboard units controlled separately for each room by means of a individual room thermostat. But nevertheless, I think that in localities where gas heat might be the lowest in cost and still available, I think that industry should pay some attention to this trend, which I think is going to be the trend of the future, namely much smaller units than we've had in the past.
Due to better insulated homes.
Oh, right. And,
Better pump houses.
Yeah.
You'd have to make a benefit cost analysis, especially on the air-to-air heat pump, to see whether or not you would get sufficient fuel savings out of it, or energy savings, to justify a much larger expenditure in the equipment cost and the annual maintenance costs and so forth on such equipment.
Rudy, in the overhang design, how crucial is this inches of overhang and the distance above the windows for the overhang?
Well, it's an important factor.
Some of the slides.
It's an important factor. Unfortunately, Mother Nature is a little bit difficult in the fact that we sometimes get more sun than we want, and other times we don't get all the sun we need. So we have to strike a balance somewhere on this overhang in order to get maximum sun penetration, let's say in the month of February. This means that in order to get that, why we may have more sun than we want 6 months away from that, when the sun angle is higher, but it still is penetrating too much. So we may have to have some adjustable overhangs in the most severe cases. The overhang that was selected here seemed to have provided the best compromise between the two situations of summertime and wintertime. Along the line, though, of the sun control, I think that there is one point about this that we must emphasize. There's a great deal of thought today among the general public that windows are losers, and we're losing all this heat throughout the window, and therefore the solution is to cut out the windows. And we even have people talking about it, building underground houses and so forth. Well, as pointed out in the film, it's very necessary to have light and be able to see out and so on. But Wayne has developed through his studies of the solar angles and the input of the sun a very convincing proof that south windows, and particularly triple glass windows, in this central climate that we're talking about here, are really winners, that we gain more heat through these than we lose. And we have proven this also by means of the computer program. Just to demonstrate this to our own satisfaction, we ran this house with the Indianapolis weather tape as designed and found that the heat requirements, the fuel requirements, were around 9 million BTU per year. And then we said, okay, let's close off all the south windows. Let's get rid of those windows. Make it a blank wall. We then found that we needed 12 million BTU per year to heat the house. So the south windows are winners, and that's the whole premise.
Provide a net gain for the whole heating of the heating system.
Exactly.
Considerable.
So those people that are concerned about too much glass in their house, they should be more concerned about what kind of glass it is and where it's located.
The orientation of that glass.
Right.
You're speaking here of triple glass, which most people don't usually think of, and as contrasted with double glass in the form of a single glass window and a storm window. Where is this second?
Well, we proposed
third plate of glass.
We proposed to do it in a relatively simple manner. It is quite possible, readily available now, the welded insulated glass windows. Well, there's 2 layers. Then we use the storm window as the 3rd layer.
Which helps.
Now, any of these things that we're talking about here, as far as the architectural features of the house are concerned, are here now. We don't have to wait for any developments on this. We don't have to wait for somebody to set up standards and measurement techniques for the performance of these things. They're already here. It's today's technology.
Well, the advantage of that, of course, is that if you can save a tremendous amount of energy just by using the house itself, both from thermal and solar benefits, is that when the day arrives that you can buy solar hardware systems to adapt to this at a reasonable price where the benefit will be commensurate with the cost, you can put it on. There are any number of things that we would use in this house if we could get the benefit for the investment.
Wayne, I'd like to bring up one point that Rudy sort of introduced. I find very interesting the double wall construction that you've specified. I was wondering, rather, can you tell whether or not the ordinary carpenter is able to provide such a wall with his existing knowledge?
Sure. This is a common technique. It has been for several decades. It's been used in multifamily dwelling and for sound walls. This is nothing new to it at all, or plumbing walls, what have you. The other thing is we've had some comment, well, how come you have such a large wall? Would that cost you a lot more? Of course, Rudy and I have built dozens of houses with walls that are much thicker in, say, brick veneer, but with nowhere near the thermal performance of this wall, which is 2.5 times the thermal resistance of a, say, brick veneer on 2x4 stud.
Well, you brought up the sound wall. I assume you mean an acoustic value in that wall, and it seems to me this house would have very good acoustic characteristics.
Yes, I would think it would be, up above the 50 range. And another advantage, of course, of the double wall is that you can vent any moisture that gets into the wall to the attic through this continuous slot.
Some of the illustrations in the council notes, which the listeners will have available along with this tape, I think bring out some of the design features of the wall, particularly. There's some.
There is one design feature of the overhang that is different from ordinary, and we have raised the soffit of the overhang, the underneath part of the overhang, in normal design is immediately above the window. We've raised it to the level of the ceiling of the inside of the room. In doing this, the shade line is placed in such a manner that we get full benefit of the sun in the wintertime. Ordinarily, with the overhang down low, you don't get any sun on the top of your window, but we do in the wintertime. The other big advantage of this is that it gives us enough room to get an adequate amount of insulation in the attic. Ordinarily, under current construction practices, this is difficult to do. And sometimes it's done incorrectly and creates ventilation problems and subsequent moisture conditions in the attic.
You just have to get that moisture out of there.
Oh, yes.
Very important.
It's also important, of course, to reduce the attic air temperature during the cooling season. Keep the attic temperature down.
Now that
like
you
to s-
mention the
Go ahead.
Now that you mention the cooling season, let me bring out one very interesting feature as far as it relates to the mechanical engineer. The cooling load, I understand, is of the order of 12,000 BTU per hour. Now that may not mean much to the ordinary homeowner, but this amounts to what we call a 1-ton cooling load, and is about the capacity that many window air conditioners can provide. And it's an amazingly low value, because in a normal house of 1,500 square feet, we consider 2.5 tons to 3 tons, 2.5 or 3 times the size as the initial requirement. And I think that a great part of that load is primarily just to get rid of the, or not get rid of, but to reduce the moisture content, humidification load due to the air change.
I'd like to switch back to the estimating of the total energy consumption for a season. Some of the listeners may be used to doing that using the degree-day formula that would appear in the ASHRAE guide. And if they attempt to do it on this house, they will not get anywhere near the answers that we get by a computer, because the degree-day formula is based on the assumption that the internal gains, including solar gains, are just sufficient to take care of about a 5-degree indoor-outdoor temperature difference. And therefore, you start heating the house when the outdoor temperature is 65. In this case, the internal gains may take care of a 10 to even a 15-degree temperature difference, so we aren't going to start heating this house until the average outdoor temperature is down around 45, 50, 55 degrees.
Well, this would markedly shorten your heating season.
Very much shorter, so that the degree-day formula will not apply at all. In fact, our analysis indicates that we'd have to change the 24 hours a day down to about 12.3 to make it come out right.
I think Bud has given the most dramatic description of. He says, designing a house in this manner is really like taking the house and moving it several hundred miles south, because we have a shorter heating, we have in effect a shorter heating season, a milder heating season, and therefore reduced fuel consumption.
As the house would see it.
Yes, as a house would see.
I have a feeling that sooner or later the heating and air conditioning profession is going to have to realize that you design heating equipment the same way you do cooling. We account for the internal gains in cooling equipment and provide equipment to take care of that gain because we have to.
It's part of load. Yeah.
But on heating, it's in reverse. The internal gain or the solar gain is assisting the heating system, but we never give it credit for that when we design the equipment. So we're over-designing all our heating systems.
Even without solar gain, or very minimal, your internal gain is a third of your heat requirement, or if you use more than we allowed, this very minimum amount, it could be 2/3.
Well, for the average, for the design day it wouldn't, which
No,
we have to design the
correct.
heating system for. But
Yeah.
Right.
Yes. Well, you're designing for the worst conditions, but you have to look at fuel consumption and performance.
yeah,
of
there's
the
two different
system.
bases.
Right, on a day-by-day basis for this variation of load during the heating season.
As I recall, in the case of the cooling, the 12,000 BTU design occurred only about twice in the whole
Yes.
cooling
It's
system.
the worst
The
condition.
worst condition only occurred twice.
The general maximum is around 8,000. And even on the Indianapolis weather tape, it never got over 14,000, and generally it was around 10 to 11,000 as a maximum.
One interesting part of this thing that I think many contractors want to inquire about is whether or not we are recommending vapor barriers. And I think in general the architects have specified vapor barriers, effective vapor barriers like polyethylene sheets on walls and ceilings, so that the problem in the wintertime no longer becomes one of how do we humidify the air. But I think the problem throughout the year might be more of how do we control the relative humidity from getting too high. And this is why the earlier statement was made that we are probably going to provide some form of ventilation, either in the form of kitchen vents or bathroom vents. But that in turn brings up another auxiliary problem. How do we get the air then to come into the house if we provide a bathroom vent or a kitchen vent? And I am sure that somewhere or other we're going to have to provide a small duct that provides outdoor air to come either into a warm air heating system or into the case of the hot water system, bring it in somewhere or other into the room without creating any drafts. Now, some contractors, you might say, insist that we should not have vapor barriers in the ceiling. Their idea being that the moisture should escape from the room naturally. But I think the experience at the council has been very negative in that respect, because any moisture that gets up through that ceiling and penetrates the insulation is then going to condense into in the attic someplace or other, and then we have the possibility of actually getting drippage.
Indoor rain.
Indoor rain.
We have some pretty good horror pictures of mold growing in the attic too, where this ventilation has been
Where the
inadequate.
vapor barrier has not been properly installed.
Right.
That's an important concept. I think the locale plus the solar features of this home make it a very exciting operation when you think you can heat 3 homes with the same amount of gas per year that the rather well-built HUD home provides or requires. This is a very exciting operation.
Yes, that's a point that we really haven't made too well here. We've talked about our comparison with the HUD home. Now, the HUD home is really an excellent home.
Yes.
This is a home with full thick insulation in the standard wall, with 6 inches in the ceiling and provisions in the floor and so on. And there aren't many houses that have been built up to the HUD standard. So if we move back in time to the when our 60 or 70 million housing units have been built, we'll find a very small percentage of those even at HUD standards, so that the saving possibilities over the older houses is even more dramatic than what we see here.
Of course, we would love to build this house, the locale house, and the HUD house, side by side, under the same climate conditions, monitor them, take careful readings on what happens, control the internal loads to be equal, and then try some various changes in the design and different equipment. The water-air heat pump, the air-to-air heat pump, the resistance heating, and so forth. See whether or not it would be economical to add even more insulation in certain climates. There are many questions to be answered which can be only done by performance testing.
I'd like to ask Warren, we've said that this is for a middle region, in other words, 4,500 degree days and greater, but what modifications do you think we might have to make if we go, say, south of the Ohio River or the Mason-Dixon line, which brings us into areas which have 4,500 degree days or less?
Well, the winter fuel conservation would be of lesser importance there than it is up here, and you begin thinking of conservation in the summertime. So that you'd give greater consideration to your summer loads than we do here.
And shading.
The need of the triple glass windows, for instance, I don't think we'd probably need triple glass. Double glass would
Drop down
probably
to
be
double.
more than adequate, or certainly adequate in your southern climates. And you might want to have provision for even more air infiltration or ventilation than we have up here, because you can stand it without increasing the loads appreciably, and in many instances could get the comfort desired without the use of mechanical equipment, like
Well,
ventilation.
Certainly, we would still avoid the east and west windows for
Yes.
solar gain.
Yes.
That would be avoided, and you might go to a higher percentage of north windows, not needing them for the solar gain in the winter. And of course, you would want to have a good performance of your attic ventilation. Very excellent performance there. But perhaps the roof overhang might be somewhat more, but not too much, because the sun angle is considerably higher in southern latitudes.
I know I've talked, not about this, but in previous periods, I've talked with heating engineers from the southern area, Texas and places like that, and they would object, until proven otherwise, to the use of such a high mass of insulation, because it stores the energy they get during the day that they don't want, and then they have it in the house at night when they don't want it either. They'd rather have a house that cools down rapidly when the temperature goes down. Now that would be particularly true in your dry climates, where they may have 25, 30 degree diurnal temperature change.
I always certainly want to thank the panel for your input to this discussion. I think it will help the viewer of the tapes, the earlier part of the tape, to better understand both the advantages and some of the cautionary aspects of the low-cal solar home. Thank you very much.